Alright, today we're talking about real number operations, and a set of numbers is closed under an operation when the operation performed on any two numbers in the set results in a number that is also in that set. So if we have an integer and an integer added together and the answer is an integer, that's a closed set of integers. This applies to addition, subtraction, and multiplication. So let's take a look at some real number operations and what the outcomes might be. So 12 and 5 make 17, and right now we're identifying rational or irrational. So you'll remember that rational numbers are most things. Irrational numbers are decimals. That never end. And never repeat. So 17 is rational. Negative 4 plus 9 is 5, and it's rational. 4/5 and 2/3, so let's see, that would be 12/15 and 10/15, which is 22/15. Any fraction is rational. 0.74 plus 2.1 would be 2.84. That's a decimal, but it ends, so it's rational. Three times 8, 24 is rational. Negative 4 times 6, negative 24 is rational. 3.1 times 0.6, 1.86. Again, it's a decimal, but it ends, so it's rational. And 3/4 times 5/7 is 15/28. And all fractions are rational. Alright, moving on. When we have sums of rational and irrational numbers, we're going to take a look and see what happens. 1 plus the square root of 5. Well, the square root of 5 can't be broken down into anything different, so that's just 1 plus the square root of 5. It can't be broken down anymore. There's no perfect square I can take out of that. So it's irrational. Because you'll remember that square roots of non-perfect squares are always irrational. So the square root of 2 plus 5/6. There's nothing I can do with that. So once again, I have the square root of 2 plus 5/6. And it's irrational because of my square root. 4 plus pi, irrational because pi is irrational. And negative 8 plus the square root of 10, I can't combine those, and there's no perfect square I can take out of that 10, so it too is irrational. So it looks like when I'm adding a rational number with an irrational number, I'm ending up with all irrational answers. Using the results in activity 1, do you think the set of rational numbers is closed under addition and under multiplication unexplained? So, taking a look back, all of our addition and multiplication problems were rational, and so rational numbers added or multiplied do make rational answers. So our explanation would just be that all rational numbers, when added or multiplied together, make rational answers. Using the results in activity 2, what do you notice about the sum of a rational and irrational number? I just got finished saying that the sum of a rational number and an irrational number seems to always end up as an irrational number. So the sum is irrational when we have one rational and one irrational number. Alright, let's see about multiplying a rational number with an irrational number. 6 times the square root of 12. So the square root of 12 can be broken down into 4 times 3. And the square root of 4 is 2. So 6 times 2 is 12 square roots of 3. And that's irrational because of the square root. Negative 2 times pi, that's simple as just negative 2 pi, and that's irrational. 2/5 times the square root of 3 is 2/5 square roots of 3, and that's irrational because of the square root of 3. And 0 times the square root of 6 is 0, which is now rational. So that was an interesting twist that we had there. Alright, the table shows several sums and products of irrational numbers. Complete the table. So 3 square roots of 2 plus 5 square roots of 2. You would use the square roots of 2 just like you would an x. So 3x plus 5x would be 8x. 3 square roots of 2 plus 5 square roots of 2 would be 8 square roots of 2. And it's irrational. The square root of 12 plus the square root of 27. Well, the square root of 12 can be broken down into 4 times 3. Square root of 27 would be 9 times 3. So this is actually 2 square roots of 3, because the square root of 4 is 2. And this is 3 square roots of 3, because the square root of 3, the square root of 9 is 3. So 2 square roots of 3 plus 3 square roots of 3 ends up making 5 square roots of 3, and that's irrational. Square root of 7 plus pi, we can't do anything to that, it's irrational. Negative pi plus pi would be 0, giving us a rational answer. Pi square roots of 7 is irrational. The square root of 5 times the square root of 2. When we're multiplying square roots, we just multiply what's underneath the radical symbol, giving us the square root of 10, which is irrational. 4 pi times the square root of 3 gives us 4 pi square roots of 3, and it's irrational. And the square root of 3 times the square root of 3 gives us the square root of 9, which is actually 3, which is rational. So here we had a rational answer and a rational answer. One using addition and one using multiplication. So using the results in activity 3, is the product of a rational number and an irrational number always irrational? So our answer here has to be no, again, because we have a rational answer. But the only rational answer that we got was when we multiplied by 0. So our answer is definitely no. We had one rational answer. So we cannot generalize that the product of a rational and irrational number is always irrational. And using the results in activity 4, do you think the set of irrational numbers is closed under addition and under multiplication? Well, we have two irrational numbers here that give us an irrational answer. Same thing for the next two, but then we have two irrational numbers added together that give us a rational answer, and down here we have two irrational numbers that give us a rational answer. When we multiply. So it's not closed under addition, it's not closed under multiplication, because sometimes when we add two irrational numbers or multiply two irrational numbers, we end up with a rational answer. Alright, is the set of irrational numbers closed under division? If not, find a counterexample. A counterexample is an example that shows that a statement is false. So, if I did irrational numbers, let's take pi divided by pi. That gives me 1. So that's rational. So I have two irrational numbers that make a rational answer. So no, division is not closed either. Is this, I did that one. The set of integers is closed under addition and multiplication. Use this information to show that the sum and product of two rational numbers are always rational numbers. So you need to show an addition problem and a multiplication problem. Using integers. So a set of integers is closed under addition and multiplication. So you're going to show that the sum and product of two rational numbers are always rational numbers. And I would use integers to do so. So go ahead and write down your two examples that show that integers are closed under addition and multiplication. Alright, have a great night.